Well, good morning. This is Monday morning, the 20th of March 2017, already 8:02 or so in the morning, and supposed to be Math 237 linear algebra class, but I'm the only one in the room, so we'll get started in spite of nobody being here. So wish you were here. It makes it a lot more interesting to talk about. Now, my mark on the page, I've got a little comment here and I can't quite make out what it means, but we were doing, just beginning section 3.2, determinants in elementary operations. We had looked at the two determinants at the top of the page, sort of, right near the top of the page, and you had agreed that obviously the second one was far easier to deal with the determinant. Now, they want us to go on and do the first determinant, okay? So we'll do that, okay? And then, well, actually, they say, I think we already did the second determinant of B, and that was just the product of the main diagonal. I think if you remember, we've already established that in the last section or somewhere before that, I believe. Yeah, on page 109, theorem 3.2, the determinant of a triangular matrix, whether it's upper triangular or lower triangular matrix of order n, is determinant is the product of the entries in the main diagonal, period. Okay, I think we had done some to show that, but it definitely was the case. So we got the determinant of B, which is 1 times 2 is 2 times negative 3 is negative 6 times negative 1 is positive 6. That's not how I would have done it. I've done 1 times 2 is 2, negative 3 times negative 1 is 3, 2 times 3 is 6. However you want to do it, okay? Now, so what we're going to do is do the determinant of A. It's only because they say to, so let's do it. I'm going to get my pen activated in the right color. Okay. Here's the determinant of A. And this is a 4 by 4. 1, negative 2, 3, 1. 4, negative 6, 3, 2. Negative 2, 4, negative 9. And negative 3. 3, negative 6, 9, 2. Okay, that's the one we're supposed to take the determinant of. Make sure I've done it right. Got it. I think that's correct. Now, how do we do a determinant? Well, we pick our favorite row or column and expand on it. Well, guess what, team? Bad news, no zeros in any position in this matrix. A 4 by 4, 16 positions. You would think the odds are at least 1 and maybe even 2 would be zeros. No, all these are non-zero numbers. So you get to pick a row or a column. And I'm just going to pick the top row. No special reason for it. The numbers are a little lower, but don't know if that really matters, but let's just do that. So the determinant of this matrix will be 1 is in the positive position, so that's going to be a 1 times the determinant of the block that's left over. They call it, I think, the minor, okay? The determinant of the minor, which will be negative 6, 3, 2, 4, negative 9, negative 3, and negative 6, 9, 2. Okay? Then we're going to do, and this is why I sort of don't like wiping them, but On this, it's easier than if you were doing it by hand. Then let's go to the second entry here. We're using row 1, okay, is a -2, but it's in a negative position, so that's going to be a +2, okay? I hope you don't mind my doing it like this. It's the way that makes the most sense to me rather than cofactors and things. That's a negative position, so it is a -2, so that becomes a +2 times its minor, if you have to call it that, which would be 4, 3, 2, -2, -9, -3, 3, 9, 2. Okay, my bookkeeping isn't looking too great, but I think hopefully we can live with it. Okay, trying to get the eraser to come up. Now let's go to the third entry. Yuck! I just wiped out my 2. Disadvantage of this. I believe, yeah, that was a -2. Yeah. Okay, now we go to the third entry. So we'll wipe out the first row, third column. Why am I ever even wiping out? Okay. That's a 3, and it's in a positive position, so that's going to be a +3 times its minor, which would be 4, -6, 2, -2, 4, -3, and 3, -6, 2. Okay? And this time I'll be a little smarter about it. Don't need to read row 1 because that's what we're using every time. So we're going to the last entry, which is a 1. Okay? But that 1 is in a negative position, plus, minus, plus, minus, okay? And it is a +1, so that becomes a -1 times its minor, which would be 4, -6, 3, -2, 4, -9, 3, -6, 9. All right. Now, what we do at this point is do our expansion of the 3x3s, which is a real pain in the neck, but it's doable. I'm going to leave some room up here, so let's do it down here. The first one is -6, 3, 2, -6, 3, 4, -9, -3, 4, -9, and -6, 9, 2, -6, 9. Okay. Now, let's do our down diagonals. That would be 54 times 2. That's the easiest way to do it. It's 108. And this is going to be a 1 there, so I'm not going to write down the 1. So it's 108. And this one's going to be a 9 times 6, positive because there's 2 minus signs. So 9 times 6 is 54, so that's a +54. Okay? And then our last down diagonal is 36 times 2 is +72. I hope I'm doing this right. Our up diagonals, which are going to be subtracted, but there's a -9, so that's only one minus sign, so this is going to be added. So that's going to be 54 times 2 again. Wow. Plus 108. Okay. My next up diagonal is going to be, it's a minus in front, okay? And then you got 2 minus signs, so that's going to be a plus. So this is going to wind up being a negative here. And what we have now is 54, 9 times 6, 54 times 3. 54 times 3 is 162, negative 162. Okay? And our final one is going to be another minus because all three are pluses. So that's going to be minus 24. Okay. That takes care of the first 3 by 3. Next is going to be a plus 2 times. So let's do this next one. A 4, 3, 2, 4, 3, negative 2, negative 9, negative 3. Clean that up because that sure looks bad. Okay. Negative 2, negative 9, and a 3, 9, 2, 3, 9. Okay. Down diagonals here. 36 times 2 is 72, and that is a minus. Okay. Next down diagonal is also a minus, 27. Next down diagonal is also a minus, and that's going to be 4 times 9 is 36. Okay, our up diagonals, that's going to be a plus because it's minus going up, but you have one minus sign, so that's going to be a plus 54. Okay. Up diagonal there would be another plus because there's only one minus sign, and that's going to be 36 times 3, 108. I believe that's right. And we decided that's going to be a plus 108. Okay. And then our last up diagonal, another plus because it's a minus going up, but only one minus sign. 4 times 3 is 12. So plus 12. All right. That takes care of this one. Now we have a plus 3 times this. And the question is, I'm going to have room enough? I think so. So this will be a plus 3. I'm going to sort of scratch some. And let's multiply this one out, or stretch it out anyway. 4, negative 6, 2, 4, negative 6. Yeah, my writing's terrible. Negative 2, 4, negative 3, negative 2, 4. And 3, negative 6, 2, 3, negative 6. Okay, hope you can read that. All right, first down diagonal is going to be a plus. 16 times 2 is 32. Next one's going to be another plus because you got 2 minuses there. That's going to be a plus. And if I can read my writing, that's 9 times 6 is 54. The next down diagonal, another plus. 4 times 6 is 24. Next, the first up diagonal is going to be a minus because they're all positive. The up diagonals are negative. 12 times 2 is 24. It's so good to see you. I hate talking to myself, no matter what it says about my mental state. Okay. Oh, 2 in a row. Nice. Today, I hope, is the 28th. Okay. And the bottom part of the alphabet showed up in fine style. Marcus is here. And Michael's here. The Williams brothers are right there. Got it. Good deal. Okay. Let's get these things. Oh, man. Switched out. days ago that is coming. All right, what we're doing, at least according to my marking the text, and y'all are here to correct me if I'm wrong, so I'm doing it. I sure don't remember doing this, and I would have remembered. All right, we're on page 112, chapter 3, determinants, section 3.2, determinants in elementary operations, and we had looked at the two determinants at the top of the page, A and B, decided that B was by far the easiest. We determined its determinant because it was a upper triangular matrix, or any triangular matrix. The determinant of any triangular matrix is the product of the entries on the main diagonal. Okay? That was from theorem 3.2 back on page 109 and 3.1. Okay? Section 3.1. That was pretty easy to do. Look at that main diagonal. There's two negative signs. That means the product's going to be positive, and 3 times 2 is 6. Done. Here's how we do it if we were doing A. Okay? And I just chose the first row to do my expansion, 4 by 4. Boy, what a pain. A positive 1 times its minor, which is there. I hope I got it right. Minus a minus 2, because the minus 2 is in a negative position, making it a plus 2 times its minor, which is that. Then a plus 3, positive because it is a positive number, times its minor, which I hope is this one, plus 3 times that. And finally, the 1 is in a negative position, so that becomes negative 1 times its minor, which is the one you see there. Okay, so I hope I got that right. Okay. Then I started expanding. Well, first, should have started this higher, but we did the expansion here. This is a 1, so I just didn't even multiply, so it's going to be a 1. And I did the expansion of that first 3 by 3 by expanding the 2 first columns again and doing my diagonals. I hope I got those right. Then we did a plus 2 here times those diagonals. Okay, positives going down, negatives going up. And then a plus 3 from this one times that expanded 3 by 3. Okay, and that's what I was in the process of doing now. I've done the plus 3 from here times, and then this is 32 this way, 54 that way, I sure hope anyway. And these are positives because they're going down, and you have even number of minus signs. Now, here we had 2 minus signs going down, so that's still plus 24. Now we started going the up diagonals, okay, and these are negative, and because all those are positive, this is a negative 24. So you tell me the next one. Okay, that's going to be a negative what? I think that was what I was in the process. No, I wasn't. Okay. It's a minus because you're going up and there's 2 minus signs. But it's 24 times 3, right? Which is 72. Is that right? That doesn't seem right. Yeah. You okay with that? Okay. And then our last up diagonal also is going to be minus because you have 2 minus signs. That makes it positive, but going up makes it negative. And that's a 24. Right? Now, before I do anything else, I notice that this plus 24 minus 24 is going to add to 0. So I'm going to get rid of those post haste. I've got one more to do, and that's the minus 1. And what I'm going to do is put it up here, if that's okay. I'm just going to put a minus in front of my parentheses, and then I'm going to expand that 3 by 3, which is 4, negative 6, 3, 4, negative 6. Okay? Which is just like we did last time, only it was a 2 in that middle one. Negative 2, 4, negative 9, negative 2, 4. Okay? And a 3, negative 6. Yuck. 9, 3, negative 6. You okay with that? I should have you telling me what numbers to put in there. Sorry. I just got used to talking to myself, so I'm continuing to talk to myself. Okay, it's just like this one, except this middle column is different, which of course throws everything off. But let's do it. Yep. 144. Thank you for having a calculator. Okay. This one will be. It's a plus because there are 2 minus what? You say 162? 162. And the last down one is also a plus. Second, 36. Okay. Now our up diagonals are going to be negative. Is what? Oh yeah. Yeah, it's a minus 36. So I'll get rid of those 2 right away. Yuck. Okay. Next up diagonal, also going to be a minus. $216. And then our last up diagonal is also going to be a minus. I'm sorry? 108. All right. Thanks for having your calculator. Okay. Now, probably keep it going in hand. Let's start doing these. Okay? Now, you're going to have to keep up with it, though. Okay? Let's start with that first one, 108 plus 54 plus 72 plus 108 minus 162. Am I going too fast? Minus 24 plus 2, open parentheses, negative 72 minus 27 minus 36 plus 54 plus 108 plus 112, plus 12, sorry. Got it? Close parentheses, plus 3 times open parentheses. I don't know if your calculator has to do with times or not. 32 plus 54 minus 72 minus 24. Close parentheses. Now I'm going to do this one without parentheses. Minus 144 minus 162 plus 216 plus 108 equal. Okay. That's the problem with this. All these calculations, all it took was a sign change or something else. That's supposed to come out to be 6. You blew it. No, okay. More than likely, some little calculation and some of all this scratch came out a little bit wrong and blew it. I'm not about to take class time to try to find it. That'll be your homework assignment. Yeah, find the error in this. Okay. It does come out to be a plus 6. But look at how difficult that was. Okay. Let's just do the first one. You add these together. 108 plus 54 plus 72 plus 108 minus 162 minus 24 equal. There's where my problem is. Okay, it's supposed to be a negative 60. Let's do that first one again. That's a 1 times 6, 3, 2, 4. All right. 3 out of 4 are here. Okay. Missing Emmanuel. Okay. Negative 6, 3, 2, 4, negative 9, negative 3. Oh, no. Right there. So minus 6. I wrote it wrong. Or else it got erased when I wasn't expecting it to get erased. So that's what messed it up. So it's only going to be that one up diagonal, and that's going to be a minus 108. That was it right there, I think. Okay. I know when I did it, I said, why is it that a minus sign? Okay. So wipe those two out. Now do it again. 54 plus 72 to minus 162 minus 24. Negative 60. Okay. Now I don't remember what you got before. Do you remember? Negative 2 something another. Yeah. Negative, positive 222. Okay? And what we just did was subtract a 108 and subtract another 108. So subtract from that 216. Still not going to be enough, is it? Okay, we must have made an error somewhere else. Let's just, again, see if we can find it quick. Is what? 222. That's positive 60. Oh, yeah. No, positive 6. Yeah, right. I'm sorry. I was saying positive 6. Yes, that's where our error was. Okay. Positive 6. Okay. Right in the very first one. Very first thing I wrote down. Okay. So you see how much easier it is. Now, the other thing that we were to note was that B that we didn't write up here, but it's in your book, is you get it, and remember when we're doing the upper triangular or any of the triangular matrices, at least in this section, okay? And at the top of page 109, 3.1, recall from 2.4 that a square matrix is upper triangular when it has all 0 entries below its main diagonal, lower triangle, blah, blah, blah. Okay? The find of the, okay, now that's, okay. Well, we'll have to go back to how we gathered, and I think that's in 2.4, so let's go back there just quickly. Okay. When you're doing triangular matrices, where do we first do it? Okay. Okay. If a square matrix, this is on page 80, top of the page, I think this is where we want. That first paragraph. If a square matrix A Rho reduces to an upper triangular matrix U using only the row operation of adding a multiple of one row to another row below it. Okay? That was a caveat we had there. It's a real, we take out two of our possibilities. We can't exchange two rows, and we can't divide a row. We just use the adding a multiple of one row to another row. That's the only one we use, okay, to get our triangular matrices, upper or lower, okay? Now, they note this, and let's go back and do it, okay? So we got the same result. So what we're going to do now is erase that, and all the rest of this. Okay, we got our result. We don't want it anymore. Hopefully you got it as we were doing. Okay, I'm erasing too soon. Sorry. Were you getting some of this? I'm sorry. I'm sorry. I wasn't paying attention. How much more? I'll get these. That's just my chicken scratch before Nigel came in with his calculator. That'll be enough for now. Okay? So what I'm going to do is do row reduction on this. Now this says determinant. Forget about it being a determinant. Think of it just as a matrix now. Okay? But thank you for being a 1 there. If that wasn't a 1, we're in serious trouble. Okay, but we could do it. What are we going to do to row reduce and get zeros below it? -4 times row 1 plus row 2. Right? Now I'm going to still keep this as a determinant. I shouldn't, but yeah, that's what we're starting as. So we're using row 1, so we write it down. 1, -2, 3, 1. Yuck. Okay. Now, what's our new row 2? 0, 2, second, negative, did you say something? -9, okay, I can't hear. Okay, it got really quiet, okay. Second? -2, got it. I don't hear well. Okay, how about the next one? Okay, what will that give us? 0. Yuck. Another 0. They picked one that was hard to do determinants of, but it sure is easy to row reduce. Okay, next. Say again? Okay. What's that? What about it? Do you need it? That's just how I did the determining the determinant of those 3x3 matrices. Yeah, if you already know how to do it, you don't need to do that, but it's up to you. Okay. -3, all right. All right. And -1, perfect. Okay. How about that fourth row? -3, row 1, Okay? What will your first entry be? 0. What will your second entry be? 0. Aren't they nice? What's your third entry? One more time. 0 again, right? Right? -3 times 3 is -9 plus 9 is zilch. And the last one? -1. Got it. We have B, right? Isn't that exactly what their number B was? And we've already determined. So what we did, we reduced A to a triangular matrix. We happened to do an upper triangular there. Only took us 3 steps, but every one of those steps was multiplying, adding a multiple of one row to another row. Thank you very much. Okay? Now, that's what we're going to look at next. Okay? In example 1. So, wait till you finish all this. What's that? Okay. All right. Thing is slow. Okay, here we go. Here's example 1. Start with the determinant of this matrix A. It's going to be 2, -3, 1, 4. That one should be a piece of cake. What is that determinant? Say again? 11. Exactly. Right? Everybody agree? Let's do the determinant of B, which is 1, 4, 2, -3. Now, before we do that determinant, I want to ask you a question. How is A related to B? Yeah, we exchanged 2 rows, which is a legal elementary row operation, right? Perfectly fine. Let's see what it does to the determinant. -11. Okay, now it does it on that one.
So I have a question.
Yeah.
But someone here that
Wednesday. Okay, we're doing determinants now. They are matrices, but we're doing determinants of a matrix. And that's what the straight lines mean. We're doing determinants. Okay? And you remember how to do it for 2 by 2? Okay, good. Yeah. Now, let's look at the B example here. Okay? Here is determinant of A. Why they couldn't have used the same one, I don't know, but they just wanted me to write again. 1, -3, 2, -4. What's the determinant of that one? 2. Okay? Now, let's do the determinant of B, which is 1, -3, 0, 2. Now, before we do the determinant of it, how do we get B from A? Is there any relationship there? Well, the top row is the same, right? So what would have happened if we had done what we would typically have done, -2 row 1 plus row 2? That sure would have given you a 0 at the first one, wouldn't it? Okay, what would it give you for the second? 2. So that's what we did. Another elementary row operation. Very legal. What's the determinant of that one? Say again? 2 also. All right. Now, this doesn't prove it, but at least it shows it, that when you do a multiple of 1, the 3 elementary row operation, exchanging 2 rows, that's going to negate your determinant. At least in that example it did. Okay? Adding a multiple of 1 row to another row, that's going to keep your determinant the same. Doesn't change it. And that's why when you do your, and by the way, that's a triangular matrix, isn't it? So its determinant is the product of its diagonal, plane diagonal. 2, right? Okay. Now, so when you do only that elementary row operation, many times as you want to do it, that gives you, it doesn't change your determinant. All right. Man, my head is clogging up. I don't know why. Let's do a new A. 2, -8, -2, 9. Okay, what's its determinant? That's what's 2? Yeah, you're right. Now, if I were going to ask you to do an elementary row operation on that, what would be the first thing you would do to this one to get to the new B? Not yet. I want a 1 at the top. You're absolutely right. If I were doing this, you're right. I would add that first. Then I would worry about getting the 1 at the top. But we're not going to do that yet. We want the 1 at the top. Yes, divide the top row by 2 or multiply the top row by a 1/2. Okay? And what will that give you? 1 minus 4. -2, 9. What's the determinant of that one? One. Okay. Now what do we do? Elementary row operation here was row 1 divided by 2 is a new row 1. Right? Well, what do we do here? We got our determinant and divided it by 2. Now, these are just illustrations. They don't prove anything, but they do show you exactly what the thing is. Our 3 elementary row operations, exchanging 2 rows, negates a determinant. Adding this multiple of 1 row to another row keeps the determinant exactly the same. Okay? But multiplying a non-zero, a row, and frankly, or a column by a non-zero number is going to multiply the determinant by that same non-zero number. This was a 1/2. That one's the determinant is multiplied by 1/2 as well. All right, so that leads to the following theorem. That was just illustrations of it. Here we'll actually state it as a theorem. Elementary row operations and determinants. Let A and B be square matrices. Done. Okay? Now, here's the thing. When B is obtained from A, okay, by exchanging, they call it interchanging. Exchanging is easier to write. 2 rows of A, okay, then the determinant of B is equal to minus the determinant of A. If that's all you did was exchange 2 rows, that's what happens. Now, it doesn't have to be 2 adjacent rows. You might think, oh, but that's because they're 1 apart and that's going to change that. No, any 2 rows. The first and the third, the first and the fourth, the first, second and the fifth. You know, if you exchange 2 rows, you're going to negate your determinant. Okay? Done. Okay? Number 2. Okay? when B is obtained from A by adding a multiple of row A to another row A, to another row of A. What does that do? Determinant of B, what you think? Exactly the same as the determinant of A. Does not change your determinant at all. Okay? Number 3, when B is obtained from A by multiplying a row of A by non-zero constant C, okay, what you think is going to happen to the determinant? The determinant of B will be what? Is what? C times the determinant of A. You multiply the determinant as well. Okay, they do a little proof. Okay, they do it for a 2 by 2, which basically we've already illustrated, and that's a pretty simple one. So here, theorem 3.3 provides a practical way to evaluate determinants. To find the determinant of a matrix A, use elementary row operation to obtain a triangular matrix B that is row equivalent to A. For each step in the elimination process, use this theorem to determine what happens to your determinant along the way. Okay? So let's do example 2. And by the way, there's a little blurb here on the inside margin on Augustin Louis Cauchy, I think is how you pronounce his name. He was the first to rigorously define limits. Thank you very much. We love them. Continuity, convergence of infinite series. In addition to being known for his work in complex analysis, he contributed to the theories of determinants, differential equations. Interesting to note that Cauchy's work on determinants preceded Cayley's development of matrices. So they didn't even have matrices when Cauchy was working on determinants. I'm not sure how they defined them, but anyway. So let's do example 2. I think I'll erase this. Is that okay? Got it. Okay. Evidently, Nigel didn't like Cauchy, so he left. No. Okay. All right. Find the determinant of A. That's all they say. Here is matrix A, written as a matrix. 2, -3, 10, 1, 2, -2, and 0, 0, -3. Now, they said find the determinant using elementary row operations. Okay? Would you do that if that's what I ask you to do? Frankly, I wouldn't. Okay? Because look at that. You got a row with 2 zeros in it. So I would go straight to this one. That's in a positive or negative position. Everything on the diagonal is always positive, right? Plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus, plus, minus, plus, minus, plus. I don't even know how you get there. That's always going to be positive. Positive position. So you keep the -3 and multiply it by the determinant there. What is the determinant here?
So 10
Yeah, the determinant of that matrix, because you have two zeros in that bottom row, it would be minus 3 times the determinant of what's left over when you wipe out this row and that column. What's left over? Say again? 4. Say again? 7. Minus 3 times 7. Okay? And that would be minus 21. Okay? So we know what the determinant is.
So that's anytime the determinant of like 3 by 3?
Okay, yeah. Anytime you have a bunch of zeros in a matrix, find the row or the column with the most zeros in it and take your determinant from that. Okay? So use this entry here and find the determinant just with that entry. So everything else is a 0 there. So it's a minus 3 because it's in a positive position. And then you do the determinant of the minor that's left over. 4 minus a minus 3 is 4 plus 3 is 7. So the determinant of that matrix is minus 21. Okay? That just gives it to us. But now let's do what they said. Okay? And what they said to do it by using your elementary row operations. Okay? Now, what would be the first elementary row operation you would do? Exchange the top two rows? Is that what you said? I would do that too. So this would become 1, 2, minus 2, 2, negative 3, 10, 0, 0, negative 3. Don't mess with that. All right. Now, because you exchanged two rows, what did that do to your determinant? You made it negative. So keep that in mind. You've negated the determinant. Okay? What would be the next thing you would do? Negative 2, row 1, plus row 2. Okay, let's do that. 1, 2, minus 2, and 0, 0, minus 3. They stay the same. You do new second row. What does that become? 0, negative 7. Say that again. Negative 14? 14, okay, all right. 14, okay. 2 plus 10, 14, okay. Now, can you tell me the determinant of that matrix? That's what kind of matrix is that? Upward triangular. So what's the determinant of any triangular matrix? The product of its main diagonal. What is the product of the main diagonal? Second? Okay. 21. But we negated 1, so that makes it minus 21. So, yep. So, actually on this one, it was easier to just do it the old way. But it wasn't bad doing it this way either. That was an easy first step, but you remember, negate the determinant because of that. Next one was multiplying one row by, adding a multiple of one row to another row, which doesn't change the determinant. So you wind up with exactly the same determinant. Okay? Whoa. All right. Did they do it the same way we did? Okay. Now notice their way they wrote it. When they did the row reduction, so let's back off and do what they did. Okay? They went straight to determinant notation. Okay? But they did row reduction in it, which is sort of what we did too. So they're doing the determinant of A will be the determinant of that without taking the determinant. But when we went down here to this one, because we exchanged two rows, that made it the minus determinant of that. Then because we did the adding a multiple to another, we didn't change the sign, didn't change anything, so that stayed that, so this became minus 21. So yeah.
So if you change 2 rows to become
The determinant becomes the negative of the previous one. Just the determinant. If you multiply one row by a non-zero constant, you multiply the determinant of the first one by that non-zero constant as well. But if you add a multiple of one row to another row, it doesn't change the determinant, so you leave it alone. Okay. Now, I've already said this, now they're getting around to saying it, though they have actually mentioned it a time or two before. Although Theorem 3.3, which we did at the top of page 113, stated in terms of elementary row operations, the theorem remains valid when the word column replaces the word row. Okay? Operations performed on columns rather than rows of a matrix are called elementary column operations. And the two matrices are called column equivalent. Before we called them row equivalent, now they're column equivalent. When one can be obtained from the other by eliminating column operations, by elementary column operations. Okay? Now, time out. If this matrix is representing a system of equations, you can't do column operations on that. This is only when you're dealing with determinants. Okay? Do you do these column operations? Okay? So get that in mind. So let's look at what they do. There we go. I can't get it to erase. Sorry. My head is clogging up again. Here's a determinant of a matrix. 2, 1, negative 3. 1, no, that's a 4. I can't read. 4, 0, 1. 0, 0, 2. Okay? Now, if all you're interested in is the determinant, then just do it, okay? Now this one has one column with only one number in it, other than 0, and one row with only 1. That's the easier one. If I were doing this, wanting to find the determinant, I'll wipe out that row and that column. That 1 is in what position? Answer is either positive or negative. Negative position. It's in a negative position. That's going to be a -1 times the determinant that's left. So what would that be?
Can you explain something?
Say again?
How do you know, like, if it's in a positive or negative position?
Okay, that's the thing we did before. Plus, minus, plus, minus, plus, minus, plus, minus, plus.
Plus, minus, plus.
Yeah, as long as you're going horizontally or vertically. Don't go diagonally. Horizontally or vertically. Plus, minus, plus, minus, plus, minus, plus, minus, plus. Or any way you want to. Plus, minus, plus, minus, plus, minus, plus, minus, plus. It doesn't matter how as long as you're horizontal or vertical only, when you just change signs everywhere you go, even if you back up on yourself, it's still okay. That's what you do. So this is a minus position, plus minus. Okay. So it's a -1 times the determinant of what's left, and what's that? 8. So -8 is your determinant. Okay, we know that. Okay, so let's write it down. Determinant of that. Not supposed to do it this way, but that's the easy way to do it. Okay, -8. All right, now, the question is there some other way you can do this? Well, they say, what about exchanging those two columns? Elementary column operation. What's that going to do to your determinant? How? Oh yeah, interchanging two columns. it's going to negate your determinant. Okay? So what we're going to do is, this is going to be produce, actually equal to, minus the determinant of 1, 0, 0, 2, 4, 0, negative 3, 1, 2. Right? By exchanging those two columns, this is what you get, right? Now, since you're doing determinants, that's going to negate your determinant. Okay? Now, what's the determinant of this one? You know what kind of matrix that is?
What did you just change the two? Because
Yeah, I exchanged the two things, so that's going to negate your determinant.
so I had like,
Yeah, this is going to be an 8 again.
I
So
was
that's
talking about
a,
the middle row. Like what happened?
huh?
I was talking about the middle. It's like 0, 4, 1. It's not 4, 0, 1.
Okay. What I did was exchange the two columns. Now we're doing column operations, not row. Column 1 exchanges with column 2.
Okay.
Okay, that was our thing. We just exchanged the column, which negates your determinant. Since you're dealing with determinants, you can do those. That negates your determinant and your determinant here, because that's now an upper triangular matrix. Let's do the determinant of the diagonal. I mean, the product of the diagonal. 8 minus 8. Yeah, same thing. So,
Okay.
yeah. Okay. So that certainly worked in this case. All right. Now, one that's a little nastier, perhaps.
It's only for the determinant.
Only with determinants can you, well, I mean, if you think about it, though, even if this were an equation, all you're doing is rearranging the order of your variables. But you have to remember that's a new, that's now your x2 rather than your x1, and that's your x1 rather than x2. So really, you could do the same thing, but then you have to keep up with your answer. If your answer is x1, x2, now it's x2, x1, x3, So we usually don't do that when we're solving equations. You could, it's legal, but we just usually don't do it, because then you have to keep up with how many times you've done this, and it could be hairy, and you wind up with exactly the wrong answer. All right, let's do a second one. Can I go on and delete this one? All right. Now again, determinants only. 2, 3, negative 5. 4, 1, 0. Negative 2, 4, negative 3. Now, this one only has 1 0 in it. So the only thing, if you're going to do it brute force the old way, actually what I would do is the 3 by 3, I would expand it anyway. Okay? But there's nothing easy here. Okay? Now, I'll admit to you, I'm so used to doing row reductions, I'll look at those rows and almost throw up my hands and say, not much you can do. Because this doesn't have any 1s in it. You can't divide any of those rows by 2 or 4 or anything else. And it seems like, yeah, what a pain. But what you could do, look at the columns. What's the first obvious thing you can do to a column? Yes, divide that first column by 2. So here's your column operation. Column 1 divided by 2 is a new column 1. Okay? So this would produce, now, you're multiplying by 1/2. So this is going to be 1/2 times, what do you get here? Because you're doing determinants now. 1, 2, negative 1. 3, 1, 4, negative 5, 0, negative 3. All right. Now, at this point, it's up to you what you want to do. Frankly, there's nothing that pops out at me that screams and says, do this. So frankly, I would just now go back to row operations. And what would you do first? Unless you can see something better, what would you do first? Pick something. That would be fine. I would get rid of the 2 too, right? Okay, so let's do both of those. The first one would be, how will you get the 2 to become a 0? That will make it a 1. We want it to become a 0. Okay. Negative 2 row 1 plus row 2, right? It becomes the new row 2, right? And then the one you've been wanting to do, what would you do to that? Row 1 plus row 3. Got it. So let's do this, okay? Now you're still going to have the 1/2. Don't forget that. You're going to leave row 1 alone. 1, 3, negative 5. Okay? What's your new row 2? Zero. That's why we did it. And by the way, doing this operation doesn't change your determinant any. That's why we just left the 1/2 just like it was. Next. Say again. Negative 2 row 1 plus row 2, right. Negative 5, right? Negative 2 times 3 is negative 6 plus 1. Negative 5? Yeah. Next. Yep. Right. Plus 0 is still 10. Okay? And then the one you've been wanting to do. 0. What's that? Is 7 and negative 8. Okay, I'm not liking this too much. Are you? All right. Pain in the neck here, but real big pain in the neck here. You really need to get, well, actually, if it were me, I'd stop right here and do my determinant. You don't have to get it in upper triangular form. That's nice, but that's going to be a pain. So I'm going to stop right here and do the determinant. It's 1/2 of, and what will I use? The first column. 1 is in what position? Plus, so it's 1 times the determinant here. What's your determinant there? Yep. 40, which is negative 30, and 1/2 of negative 30 is negative 15. Okay, that should be the determinant. Now, I'm pretty sure that's not the way they did it. Wait. They didn't do it. They just stopped. Okay, now the only thing they did though is this isn't consistent with what they did before, is it? Okay. They're saying factor out a 2 of the first column, and before it looked like they were when B is obtained from A by multiplying a row of A by or row or a column by a non-zero constant, then the determinant of B is C times that determinant of A. Okay, they're doing it backwards. Okay. So I think this actually becomes, sorry about this, the way they're wording, and I really don't like the way this book does this. This is actually a 2 here, so this will be a minus 60, okay? They word it one way in one thing and then turn around and do it something else. They factor out a 2 here, keep that, so it's negative 60, okay? I was trying to do it the way they did in the theorem, but then they reversed the 1. So it's 2 times, or 1/2 times the determinant of A, which would be 2 times the determinant of B. Sorry. Okay. I should have caught that. They do it one way, and then the example does it the other way. All right. Unfortunately, we're out of time. Sorry about that, especially since I messed up that last one. Okay, we will start next time with example 3. However, we did get far enough along for you to do some homework exercises. So do any of the odds 1 through 19. Okay? Those I think are pretty easy. Then do either 21 or 23, or both if you choose. And then do any of the odds 25 through 35. Okay?
Okay, show me one more time how you got the like I get how you got to 40, but then you subtract it from like -7.
Say again now? Oh. Okay, they didn't go this far. That's why they quit, okay? But what you do here, what you did was half of this, so half of the determinant of this one would be the determinant of that, which is the same way of saying twice the determinant of this is that. So the easier way to look at it is factoring out the 2 outside the determinant. So that's what they did. Now, once you then do these row operations, that doesn't change the determinant any. And once you have a row or a column that only has one non-zero entry, use it, okay? Here we have this row, this column here. So wipe out that row and that column, and it's in a positive position 1 times the determinant of what's left.
Okay.
Yeah. That would be 40 times the negative 70, it's minus 30. The 2 in front makes it a minus 60. They didn't take it. They didn't go that far. I was doing it thinking it was going to be pretty easy. And it wasn't hard, but it's sort of a pain in the neck. Okay, we'll pick up and go from there next time. Good deal. So I'm going to end the